Okay, guys, Unit 3, Lesson 5 today, we're looking at solving rational equations. You'll notice as we move through this course that the units kind of follow a similar pattern. We're investigating the type of function, what it is, what characteristics are unique to it. We're graphing those functions. We are solving equations that represent those functions. We're solving inequalities that represent those functions, and we're examining rate of change. So there's some pretty consistent themes throughout the course, and we're kind of looking at doing the same thing, just applying those skills to different types of functions. So now we're looking at solving rational functions. So we'll talk a little bit about what that means. Again, we talked about this in Unit 2, but what does it mean to solve an equation? And then how do we do that when we have variables in the denominator? Okay, so lesson 5. All right, so by the end of this lesson, you can solve equations that involve rational expressions. That is the goal by the end of this unit. So I'm going to start with a little bit of a guided warm-up just as a refresher for some of us for fractions and also for solving equations. So for example, if I said, when is 5x equal to 10? This is a linear equation with a y-intercept of 0 and a rise of 5 and a run of 1. So if we were to graph it, it would start at 0 and it would go up 5 over 1, up 5 over 1, and I want to know when that is going to be equal to 2. Well, if I go up 5 over 1, then that's a 1, 5 coordinate. If I go up another 5 and over another 1, that's a 2, 10 coordinate. So we know it's going to be the answer is 2, but we solve equations using inverse operations. And so we isolate the variable by doing the opposite to try to get rid of something. And whatever we do on one side of an equation, we have to do on the other. Because if we take 1/5 of this side and we don't take 1/5 of this side, these two things can no longer be equal. So this is like throwing it back to grade 9, really, really simple stuff. But it's really important that we understand the foundation of what it means to solve an equation. And then we get our solution x is equal to 2. So then we have opposite operation if we are dealing with a number that is in a denominator or a quotient, or we're dividing by. But the same thing, if this was 5 times x and we did the opposite, which was to divide by 5, this is x divided by 5. So we do the opposite, which is to multiply by 5. But if I take 5 times on this side, I have to take 5 times on this side. This just says that some number divided by 5 is equal to 10. And that number that we divide by 5 and end up with 10 is 50. Those cancel out, and we end up with x equals 10 times 5, which is 50. Okay, so we're just looking at those basic inverse operations that you guys have been practicing for years and years. But now, what do we do if the variable is in the denominator? Because here we had 5 times x, and here we had x divided by 5. But now we have 1 divided by x is equal to 5. So 1 split up into some amount of groups is equal to 5. So we have to figure out, okay, 1 divided by what is equal to 5? And so to solve this, we use the exact same method. When we had x divided by 5 and we wanted to get that 5 out of the denominator, we multiplied by 5. But because we did it on one side, we had to do it on the other. I do not want this x in the denominator. So what if I multiply by x so I can just cancel it out? That's great. But I've changed the equation unless I multiply both sides by x. So I've got on this side, just 1 is equal to 5x, but now x is not by itself, and now I have to do my inverse operations, which is to divide by 5 on both sides, and I figure out, and I'm just going to switch the order, that x is equal to 1/5. That makes sense. If I take the number 1 and I split it up, I divide it into fifths, then I would have 5 of them. Okay, so keep in mind that a lot of the same rules apply when we are solving for our rational equations where we have variables in the denominator. We're still using opposite operations, and we're always trying to get stuff out of the denominator. So for this one, solve the following rational equation. So there's a few things. We're looking for a solution. We want to know when this rational function, 6 divided by x plus 3, is equal to exactly 2. So what does it mean to solve? It means if we had this rational function, and we could look at it on a graph, 6 over x plus 3. So I already put a bunch of these for the lesson in here. So there's the graph of 6 over x plus 3, and we want to know for what x values does this entire function equal a y value of 2? So just to recall from the last unit how we can use Desmos to solve an equation, we can put a horizontal line at the point that we are interested in. So when I put a line at y equals 2, my red function, my rational function, which is 6 over x plus 3, equals a y value of 2 right here when x is equal to 0, and only when x is equal to 0. So x is equal to 0 is the solution to this question, but of course we need to be able to solve algebraically because oftentimes we don't have graphing technology or not on our tests and things like that. So how do we do it? Well, I do not want this x plus 3 in the denominator, so let's multiply by x plus 3 so that those can cancel out. But if I multiply this side by x plus 3, I have to multiply this side by x plus 3. So what I'm left with is 6 is equal to 2 times x plus 3. And then I have to distribute. So I have 6 is equal to 2x plus 6. And then I use my opposite operations. I take away 6 from both sides, and I have 0 is equal to 2x. And then I can divide by 2, again, my opposite operations, and figure out that 0 is just equal to x. So when x is equal to 0, this rational function will have a function value that is equal to 2. Okay, so this is the function value. Now, I put this note here that says what can x not be, and we need to keep that in mind because if we go through the motions and we solve and we get one of our restrictions, we cannot state that as a solution. So remember that we're never allowed to divide by 0. We can never break that rule. So we have to consider when would x plus 3 equal 0, and that would happen when x is equal to negative 3. So our domain for this is x can be anything it wants. X can be an element of the real numbers such that, sorry, we just need one vertical line there. X is an element of the real numbers such that x cannot equal negative 3, and we just double check to make sure that the solution we get does not break any of our domain rules. And so therefore, we don't have to necessarily write a therefore, but therefore the rational function 6 over x plus 3 has a function value of 2 when x is equal to 0. 2 when x is equal to 0. Okay, so keep in mind what it means to solve, and also keep in mind your restrictions on the original rational function. Okay, so that's kind of a warm-up that I would do with my in-person class, but I went through it with you guys here. And so now we're going to start looking at some examples. So again, we cannot solve when there are variables in the denominator. How do we get the variables out of the denominator? The exact same way we get anything out of a denominator, and that's using our inverse operations. So if this is x plus 3 divided by x minus 1, let's multiply by x minus 1. X minus 1 on both sides. Okay, if we do it on one side, we've got to do it on the other because I want those to cancel out. So now I have x plus 3 is equal to 2 times x minus 1. And just to go backwards a step, remember that what this question's actually asking me is when will this rational function, x plus 3 divided by x minus 1, have a function value that is 2? That's really what we're looking for. So I do that, I get my variable out of the denominator. I now have to distribute to get rid of my brackets. So I've got x plus 3 is equal to 2x minus 2. And then I need to get my variables on one side. I could bring my variables to the left, but then I'm going to take away 2x, which is going to bring me into negative x's, and then I'm going to have to do another inverse operation. So I'm actually going to bring my variables over to the right, and I'm going to bring my numbers over to the left. So I'm taking away x on this side so that those cancel out. So then I also have to take away x on this side, and I'm adding 2 on this side so those cancel out, but then I have to add 2 on this side, and I'm left with 5 is equal to x, or x is equal to 5. So therefore, let's just call this function f at x. Therefore, f at x equals 2 when x is equal to 5. And again, we could check our work using Desmos. Desmos graphing calculator is a great tool. So that was this rational function here. We want to know, when does the rational function x plus 3 divided by x minus 1 equal a y value of 2? So again, I have my function, which is my blue line, or my blue curves, sorry, and then I have my my function value at y equals 2, and that there is when my function equals a y value of 2, or a function value of 2, and that is for or at an x value of 5. And that's the only time, because we have this horizontal asymptote. So there's my solution. Okay, and again, just to double check, based on this original function, x is an element of the real numbers such that x cannot equal 1, and this satisfies that, and we're good. So that is, in fact, a solution. Okay, so here we have a couple restrictions. We have this equation, and ultimately what we're trying to figure out is, when does this function equal this function? So we have two restrictions here, because we can't divide by 0 on either side. This function can never have a denominator of 0, but this function can also never have a denominator of 0. So there's going to be two x values that are absolutely out of the question, are not possible solutions for this equation. So we could say that x is an element of the real numbers such that x cannot equal, from here, negative 3. Okay, x cannot equal negative 3, and over here x cannot be 0. So we'll keep that in mind as we go through our solutions, that we cannot have either one of those as our answer. Okay, so now we have variables in the denominator on both sides. So I want to get rid of this x here, which means I need to multiply by x. I'm doing this the long way. You guys are going to see how to do this a little faster. Because I want to get rid of that, I have to multiply by x there, so I also multiply by x there. So those are going to cancel out. So I've got x minus 1 is equal to x times x plus 1, all divided by x plus 3. So again, I still have variables in the denominator. I do not want that. So I need to multiply by x plus 3 on this side, so I can cancel those out. But that means I also need to multiply this side by x plus 3. So what I'm left with is x plus 3 times x minus 1 is equal to x times x plus 1. Now what a mess. How are we going to solve this? Well, we're going to get rid of our brackets and see what we're left with. So we've got x squared. The other way you could think about this is a simple trinomial where these two numbers add to the middle number and multiply to the last number. So you might be able to jump straight to say, okay, x squared, 3 minus 1 is 2. So x squared plus 2x minus 3. 3 times negative 1 is negative 3. 3 minus 1 is positive 2. So these two things are equivalent. This is the trinomial that matches these factors. And on the right-hand side, I have x times x, which is x squared, and I have x times 1, which is just x. So just like when we were, now we're back to solving polynomial equations, right? We've got a quadratic on both sides, so we need to isolate everything to one side. So we're going to take away x squared and take away x on both sides. And something really beautiful happens here is that the x squareds cancel out. And so we have two x's and we're taking away an x, which means we just have x minus 3 is equal to 0. And because what we're left with is a linear, we can actually just, again, use our inverse operations and bring that negative 3 over using our inverse operation and figure out that x is equal to positive 3. So again, never lose sight of what the question was actually asking. If we wanted to go back here, and let's call this function f at x, just to make it the solution easier, and let's call this function g at x, we could then say, therefore, f at x, you could say two things. F at x is equal to g at x when x is equal to 3, or you could say, therefore, f at x and g at x intercept, right? Because when they're equal to each other, that's a point of interception. Intercept when or at x is equal to 3. Okay, so again, check our work using Desmos. We had x minus 1 over x and x plus 1 over x plus 3. And we're not interested in y equals 2 anymore. We're interested in where do these two functions intercept. And if we zoom in and also if you click anywhere, the point of interception will highlight. So there it is. They are intercepting at an x value of 3, and at that time they both have a function value of 0.66. And if we zoom in really, really, really close here, you'll see that point of interception happening right there at x is equal to 3. Green is below, and then green is on top, which means they've had a point of intersection. And on the other side, it looks like you're like, oh, well, they're going to intercept over here as well. But note that purple is on top of green, and we could scroll really, 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 really far down. Let's just go to like 100, and if we zoom in, purple is still on top of green. Okay, so they're not actually intercepting. They're riding really close to each other, but they're not intercepting at any other point. We found the only possible solution. Okay, pretty neat stuff. Of course, there's a few other trickier examples. So now what? Now we have, when does this rational function combined with this rational function equal 2? And we really haven't looked at combining functions, so it's a bit interesting that we have this idea here, but we do have a lot of practice questions like this in the textbook, and really it just comes back to some simple fraction rules. So similarly to how we did kind of this guided review in the warm-up, we're going to do something similar here to recall, like, what do we do here? How do we combine those two things? So we know that if we had x over 6 plus 2 over 6, so some amount of 6's or 6 plus 2 6 is equal to 3 6. Well, we know that x must be equal to 1. Okay, but we could also use our fraction rules, which tells us that we can combine fractions that have a common denominator. So then we could say x plus 2 over 6, right? We've got x plus 2 all over 6, we've combined them, is equal to 3 over 6. And since they are both a denominator of 6, I mean, there's a few things. We could just drop the denominators and say, okay, when is x plus 2 equal to 3? When is all of this equal to all of this? And ultimately what happens is we would multiply by 6 on both sides to cancel those out. And when we multiply by 6 on both sides, these also end up canceling out, and we're left with x plus 3 is equal to 3. So when we do that, we get minus 2, and we get our answer x is equal to 1. Okay, so this is like our most basic, simplest question. We combine our two numerators, and we're allowed to do that because the denominators are the same. Okay, so then we have this situation. Now what? Some amount of 6's plus a half is equal to 5 6's. Well, we can't use this approach because the denominators are not the same, but what we can do is, sorry guys, we have an announcement for photo day. What we can do is make them have a common denominator by multiplying this fraction by 3. And remember that it still has to represent a half. So if I have x over 6 plus, 1 times 3 is 3, and 2 times 3 is 6. 3 6's is still a half. So I've not changed anything. I've just represented it different, and this is equal to 5 6, and now I can use that method and say, okay, well then x plus 3 over 6 is equal to 5 6, and now I can say then x plus 3 must be equal to 5, and I subtract 3 from both sides and say that x must be equal to 2. So 2 6's plus 1 half is equal to 5 6's. We know 1 half is 3 6's. That makes sense. 2 plus 3 equals 5. Okay, so we've got 2 more here. What happens here, I was able to just change one of the fractions to make it look like or have a common denominator with the other fraction. Here I can't do that. There's nothing I can multiply 3 by to easily turn it into 5. So when this happens, we need to find a common denominator, and in this case that common denominator is 15. And so to turn a 3 into a 15, I'm actually multiplying it by 5. And to turn a 5 into 15, I'm actually multiplying it by 3. So I end up multiplying this fraction, top and bottom, by the denominator of this fraction. And I end up multiplying this fraction, top and bottom, by the denominator of that fraction. And the result is 5x over 15 plus 3 over 15 is equal to 13 over 15. And then now, again, we can combine these, and we could rewrite it and say 5x plus 3 over 15 is equal to 13 over 15, and therefore 5x plus 3 is equal to 13. And the answer is 2, but we could take away 3 from both sides, so we get 5x is equal to 10, and then we can divide both sides by 5, and we get x is equal to, not 5, x is equal to 2. Okay, so now we're refreshing all the fraction, we're flexing all our fraction muscle memory here. So now we go one step further and we have that variable in the denominator and we don't have a common denominator. But again, this is to show you that the steps remain the same, the process is the exact same. If I need a common denominator between x and 6, when I needed a common denominator between 3 and 5, the common denominator came from 3 times 5, which was 15. Here, my common denominator needs to come from x times 6, which is 6x. So if I need my common denominator to be 6x, I need to multiply this x by a 6, and I need to multiply this 6 by an x, so they have a common denominator, but anything we do to the bottom, we have to do to the top of that same fraction. So on the top of this one, I have 6 times 2, which is 12, over 6x. And over here, I have 1 times x, which is just x, over 6x. And this is all equal to 17/30. So now I can combine these. I could say, okay, well, I've got 12 plus x divided by 6x, or over 6x, is equal to 17 over 30. So there's a few things I could do here, but what I'm going to do is the same method we did in the previous example. Now I'm going to multiply by 6x on both sides, because I want to get that 6x out of the denominator. And while I'm at it, I'm going to multiply both sides by 30 as well. Kind of kill two birds in one stone. So I can get that 30 out of the denominator, I might as well. So on this side, I'm left with 30 times 12 plus x, and on this side I'm left with 17 times 6x. So 30 times 12, well, 3 times 2 is 36, so this is 360, and 30 times x is 30x, plus 30x, and 17 times 6, 10 times 6 is 60, 7 times 6 is 42, so we have 102x, and I need to get all my x's on one side, so I take away 30 x's over here. So I have to take away 30 x's over there. So I have 360 is equal to 100 minus 30 would be 70, and that's too many. So it's 72 too many, so 72x. And if I divide by 72 on both sides, I have 360 divided by 72. I'm drawing the line at mental math there, is equal to 5. So 5 is equal to x. Okay, so that is the algebraic solution, and you guys might have already known the answer to that because of this 30. You might have said, well, the common denominator, this must be a 5 because 5 times 6 is what's going to give us that common denominator. But there's your algebraic solution and how we can handle when we have a variable in the denominator and we don't have a common denominator. So when we go back now to this question, the same method applies. We need a common denominator here. That common denominator is x times x plus 1. In order to get that common denominator of x times x plus 1, we need to multiply each fraction by the denominator of the other fraction. This fraction, top and bottom, needs to be multiplied by x plus 1. This fraction, top and bottom, needs to be multiplied by x. When we do that, we will have our common denominator, and we've not changed anything. All we're doing is finding a common denominator. And so now And notice how like we've just multiplied by 1. Like x plus 1 over x plus 1 is just 1. X over x is just 1. So in theory, to do the same on the other side would be to multiply by 1. It's not going to change anything. So we're not breaking any rules here. We can do this. And we have to figure out, okay, we've got 3 times x plus 1 over here. And we're adding 4 times x, which is 4x. And the reason we did that was to get our common denominator, which is x times x plus 1. And we want to know when this rational function is equal to 2. So we've got to do some expanding, get rid of some of these brackets. So we've got 3x plus 3 plus 4x divided by x squared plus x is all equal to 2. And we still have variables in the denominator. So how do we get rid of that? Well, we multiply the same on both sides so that those cancel out. And now we're left with 3x plus 4x, which is 7x, plus 3 is equal to 2x squared plus 2x. And now we bring everything over. We subtract 2x squared, we subtract 2x, we do it on both sides, minus 2x squared minus 2x, and we're left with negative 2x squared. 7x minus 2x is positive 5x plus 3, and now we want to know when this function is all equal to 0. What a process. We're not done. We have a quadratic. First thing we always want to do is common factor, and negative 1 is a common factor, and I can't factor out the 2. So I've got negative 2x squared minus 5x minus 3 is equal to 0. And from here, I've got to find a factoring method. I like decomposition. So 2 times negative 3 is negative 6. So I need to split this negative 5x up into two numbers that add to negative 5x and multiply to negative 6. And that would be negative 6 plus 1. So I'm going to do 2x squared minus 6x plus x minus 3. I've not changed anything. Negative 6x plus x is negative 5x, and that is equal to 0. And this is all in brackets with that negative out in front. Now I'm going to do some factor by grouping here. So I'm going to, from the first two terms, I'm going to factor out a 2x, and I'm going to be left with x minus 3. And from the next two terms, the only thing I can factor out is a positive 1, and I'm left with an x minus 3. And really, it's because I'm not really factoring out anything. I'm just getting back 1 times x is x, and 1 times negative 3 is 3. And we have all of that there. And we say, okay, negative. Now, if I factor out an x minus 3 from both terms, I would have x minus 3, and then I would be left with 2x plus 1. And that means our solutions are x is equal to positive 3 and x is equal to negative 1 over 2. Okay, we have two solutions. And to remind you what those mean, that is when this function plus this function is equal to 2. So we could say f at x and g at x and then the function value. So therefore, f at x plus g at x will equal 2 when x is equal to negative 1/2 and 3. And again, we could check our work on Desmos. So I think I already put these functions in there. So we wanted to know when these two functions combined. We did that crazy zoom in. Zoom all the way back out and go back over here. We wanted to know when these two functions combined will equal 2. So we throw up our horizontal line there, and they will equal 2 at 3 and at negative 0.5. Look at that. Beautiful, beautiful thing. Okay, this is a funky function, and we've got a vertical asymptote here and a vertical asymptote here, and we've got something in the middle, and then we've got our ends. So, all right. Did I put an even trickier one? Wow, I did, eh? Okay, I'm going to stop this video. It's getting long, and honestly, you've learned quite enough to get started on the practice. However, this one is like a level 4 good challenge. So I might encourage you to write this down and see if you can work through it. And then come back. I'll record a second video with the solution just for this question, should you be feeling so ambitious to challenge yourself. But notice for this question is that we should always factor before we begin to solve, just in case we can cancel something out. Because if we can cancel out a factor top and bottom, that's going to make our life a lot easier when we ultimately have to do that rearranging and common denominators and everything else. If we can get rid of something, great. That's just less to have to deal with. So if you are ready to move on to practice, here are your practice questions, not these ones. And if you are trying the challenge, then come on back for the second video to see the solution.